So if you look up here, you'll see that all the boards have the same correct answer. Nu is equal to C over lambda. So we know the frequency, and it's 104.3 megahertz. So mega is 10 to the 6. So 104.3 times 10 to the 6 reciprocal seconds gives us C, 3.00 times 10 to the 8th meters per second, over lambda, our unknown. So when we rearrange and solve, we get lambda is equal to 2.88 meters. Now, when you look at this, it looked like my hand was upside down, didn't it? That's weird. Okay, when you look at this, again, you have to think about the units. And in this case, we get the answer in meters, so we didn't need to change the units. In some of the problems that you'll encounter, you will have to be mindful of the units and make sure you change the units to get the correct one that you want. So now, when we talk about the electromagnetic spectrum and energy, we're talking about a wide range of frequencies. So we get energy with a wide range of frequencies, nu. And there are a lot of pictures available. There's one very similar to this in your textbook. And if you look at this, you don't need to memorize anything on here. But you can see that the energy is increasing going to the left on this picture. And here, when we have low energy, we have things like radio waves. These have really long wavelengths. Then we get to the FM radio waves, are shorter radio waves. We get to microwave energy. You're familiar with that from cooking your food. Infrared, you know that because that's the red lamps that they have in the food service that they keep your food warm. This very small range is the visible spectrum, and it's blown up here so that you can see it. And we'll be doing an experiment with this next week. Then next to the visible, it's the UV rays. That's the rays from the sun that cause the skin damage and sun tanning. Then X-rays, which can do more than just burn your skin because they can penetrate. And then gamma rays, which can really disrupt things. And my class told me yesterday gamma rays is what made the Incredible Hulk. So I never quite figured that out, how he got hulked and didn't need more gamma rays to unhulk. The other thing I could never figure out about that is how come he's not naked when he dehulks. But apparently, well, didn't you ever wonder that? I mean, every time he hulks up, he wrecks his clothes. But then when he shrinks back down, he's never naked on the show. Or not that I was disappointed or anything. Well, don't you think that's kind of odd? I guess I'm too literal sometimes. Okay. He was naked in the movie?
In the movie.
Oh, really?
Somebody asked him to pants.
Oh, I might have to check that out. Okay. I'll have to go rent the movie and see the real thing. Because on TV, he had like this crazy fabric that would expand and shrink because he was always wearing briefs or something when he unhulked. Anyway, we can look at this and we can calculate the energy. And we talk about the energy of one photon. And a photon is a little packet of energy that's produced by an electron as it moves from one area to another in the atom's orbitals or shell or cloud, however it was introduced to you previously. So we can calculate the energy, and again, it's one photon. And we know that E is equal to h nu. So the energy is h, which is Planck's constant, 6.63 times 10 to the negative 34th joule seconds. Nu is the frequency of the radiation, and you remember that nu is C over lambda, and if E is equal to h nu, then we can substitute C over lambda for nu, and so E is hc over lambda. Now, again, these are algebraic equations. So if E is h nu, h is a constant, E and nu are variables. You could rearrange this to solve for frequency. Nu is E over h. So the next time my dad called, he said, "Hey, Shorty, what's new?" I said, "C over lambda." Yeah, what else? E over h. And you know what? It sounds kind of silly, but somebody asks you in the next few days, "Hey, what's new?" People say it all the time. They don't really want to know. Just tell them, C over lambda. They'll look at you like you're crazy. But you will remember. It'll help you remember. Or maybe if it's somebody who's been around delta for a while, they're like, oh, you must be taking chemistry. So what's the energy of a photon of green light that has a wavelength of 560 nanometers? So I know the wavelength lambda. I want the energy E. And I know E is equal to h nu, which is equal to hc over lambda. So I just like to plug it all in. H is Planck's constant, 6.63 times 10 to the negative 34th joule seconds, times the speed of light, 3.00 times 10 to the 8th meters per second, divided by lambda. Now again, I've got the speed of light in meters, so I need to change nanometers to meters. 560 times 10 to the negative 9th meters. So E, my meters cancel, my seconds and reciprocal seconds cancel, and I'm left with my answer in joules. 3.6 times 10 to the negative 19th joules. That is the energy of one photon. Now, here's one for you to try. As always, go ahead, try this one with your groups on your whiteboards. Read the problem carefully and really think about what it's asking before you start chugging through.